Hello everyone, I am M.Canal-Esteve from the University of Alicante, and I am pleased to present our contribution to the LLMs for Ontology Learning 2025 challenge titled SEMA at LLMs for Ontology Learning 2025 Task C, Prompt-Decoupled Fine-Tuning on MatOnto with LLaMA. This work was carried out together with José Abreu Salas and Joan Gutiérrez within our research group at the University of Alicante. As you know, the LLMs4OL challenge provides a benchmark to explore the problem of ontology learning through 4 tasks: text-to-onto, term typing, taxonomy discovery, and non-taxonomic relation extraction. Our team focused on task C, taxonomy discovery, whose goal is to decide whether a semantic or taxonomic relation holds between 2 ontology types. We selected the MatOnto subtask, which belongs to the material science domain. It is smaller than other subtasks, which made it appropriate for detailed experimentation with limited hardware, specifically 3 A100 GPUs of 40 GB each one, shared with our research group, which requires us to schedule and distribute their usage over time. Returning to the challenge, we have seen that some works from other groups used private models capable of processing large context windows, allowing them to provide a list of terms and directly ask for the relations among them. In our case, we used a smaller model, LLaMA 8 billion, which makes this strategy unfeasible. Instead, we evaluate each possible pair of terms individually by asking whether the relation between them is true or false. Our main contribution is the finding that training with a specific instruction, such as is X a subclass of A, and then asking at inference time, is X the parent of A, yields better results than when the same wording is used in both stages. The main challenge of this methodology, when applied to this dataset, is the extreme class imbalance. There are 840 positive relations out of more than 426,000 possible pairs, meaning roughly 1 true case for every 507 false ones. This high imbalance requires strategies that emphasize meaningful negative sampling and robust generalization. Our work builds upon 2 influential approaches from the previous edition of the challenge. First, the RWTHDBAS team used domain-specific continual pre-training and task-specific fine-tuning of open-source models like LLaMA, and they enriched prompts with contextual information from external sources such as Wikipedia, showing that injecting structured context helps model infer type relations more accurately. Second, the ASKH NLP team introduced prompt engineering combined with data augmentation. They created negative examples by reversing parent-child or randomly substituting one term with an unrelated one. This approach improved binary classification accuracy and revealed that even minor variations in surface wording, like parent class versus superclass, can produce large behavioral shifts. Beyond these works, recent research by Liu et al. 2024 proposed the PTST principle, which stands for Pure Training Safe Testing. It suggests that training without alignment-specific prompts and introducing them only at test time can enhance generalization. Similarly, Sklar et al. 2023 showed that LLMs are highly sensitive to spurious features in prompt formatting, even when semantics are preserved. This insight inspired our central hypothesis, that decoupling the surface form of prompts used in training and inference might encourage the model to internalize relation semantics rather than memorize phrasing. Our methodology combines 3 components. First, parameter-efficient fine-tuning using LoRa adapters. Second, contrastive negative sampling to handle data imbalanced. And third, cross-template prompt generalization, where training and inference use semantically equivalent but syntactically different prompts. Together, these components form what we call a prompt-decoupled fine-tuning strategy. We used LLaMA 3.1 8 billion base as our backbone model. To keep the training lightweight, we applied low-rank adaptation, or LoRa. This technique injects the small trainable matrix into selected layers of the model, specifically the tension projections and feed-forward projections. Our contribution used rank R of 8, scaling factor of 16, and dropout of 0.05. The Adam W optimizer was used with a learning rate of 2 × 10⁻⁵. and the training ran with a microbyte size of 2 per GPU. We trained up to 30 epochs with early stopping after 3 epochs of no improvement, and a fixed random seed of 42 ensured reproducibility. We implemented fully shared data parallel FSDP via Lightning Fabric, which allowed us to distribute model parameters across GPUs efficiently and stay within memory limits. For comparison, we also evaluated LLaMA 3.1 or 8 billion instruct, but in our setting, it yielded lower performance, specifically in precision, though it later showed interesting recall behavior during inference. Because the dataset is extremely sparse, we had to introduce synthetic negative samples. Following the approach of SKH NLP, we created false relations by replacing either the parent or the child term while ensuring that these pairs did not overlap with gold positive. We experimented with several false-to-true ratios, 5:1, 6:1, and 7:1. The goal was to identify the balance that provides a strong contrastive signal without overwhelming the few positive examples. As we will see later, the 6:1 ratio achieved the best results. Higher results, such as 7:1, introduced too much noise, while smaller ratios reduced the amount of informative contrast. A central idea of our approach is cross-prompt generalization. During fine-tuning, we used the question, is X a subclass of A? At inference time, we changed the phrasing to semantically equivalent variants such as, is X a parent class of A or is X a superclass of A? The purpose of this prompt decoupling is to prevent the model from memorizing the training template and to push it to capture the semantic relations. In other words, the model must understand that parent, superclass, and subclass refer to the same underlying concept regardless of the wording. This design follows the PTSD framework, where the training and inference prompts are deliberately separated to enhance robustness. It also tests whether the model is capable of relational reasoning rather than surface pattern recognition. We also tested two system prompt configurations. One was generic, simply telling the model to act as an expert in knowledge representation. The other was domain-specific, framing the model as an expert in material science. Interestingly, the material science prompt consistently gave slightly higher F1 scores and more stable outputs. This suggests that expert framing helps the model interpret domain-specific relations, even when no additional data is added. So contextualizing the model's role appears to have a marginal but consistent benefit. Let's now look at the quantitative results. When we comparison the negative sampling ratios, the 6:1 configuration achieved the best overall performance with F1 of 0.144, precision of 0.109, and recall of 0.213. Both the 5:1 and 7:1 ratios performed worse, either due to insufficient contrast or excessive noise. When we compared system prompts, the domain-specific material science prompt again achieved the best F1, while the generic expert prompt slightly improved recall. Finally, the prompt pair experiments revealed the most interesting pattern. When both training and inference used the same template, subclass to subclass or parent to parent, performance dropped dramatically with F1 values around 0.04 or lower. When the training used subclass and inference used parent, the model reached its best performance, again an F1 around 0.144. The LLaMA instruct variant under the same setting achieved the lower F1 but higher recall around 0.31, suggesting a built-in bias toward positive predictions. Overall, these results confirm that prompt decoupling enhances generalization, especially when the semantic alignment between prompts is preserved. The first major finding is that identical train-inference prompts lead to overfitting. The model essentially memorizes the surface pattern and fails to generalize when facing new wording. By contrast, cross-template training forces the model to abstract the underlying relation, improving transferability. This result supports the PTSD principle and aligns with recent findings on prompt sensitivity in LLMs. It demonstrates that careful prompt variation can act as a regularization mechanism, preventing the model from relying on shallow cues. The second insight concerns system prompts. While their effect is smaller, domain-specific framing seems to guide the model's internal representation toward more relevant interpretations. Even without adding new knowledge, the prompt "you are an expert in material science" appears to prime the model towards appropriate semantic contexts. Third, negative sampling must be tuned carefully. The optimal 6:1 ratio provides balanced learning signal, enough negatives to learn contrastively, but not so many that they dominate the training process. This ratio effectively compensates for the dataset's extreme imbalance of 1 to 507. Further observation is that semantic consistency matters more than syntactic form. Cross-template generalization only succeeds when both prompts preserve the same relation meaning. If the semantics are violated, for example, training on parent subclass or subclass synonym, performance drops sharply. This indicates that models must learn relation logic, not mere linguistic correspondence. Finally, instruction-tuned models such as LLaMA Instruct show an interesting behavior. Although they underperform in F1 score, they exhibit high recall when used in inference with prompt decoupling. This suggests that instructed-tuned LLMs possess a useful inductive bias toward consistent answering, even when fine-tuned only lightly. Exploring this phenomenon under different conditions is an interesting direction for future work. Our study has several limitations. First, we were constrained to 3 A100 GPUs in a shared environment, which limited the number of experiments, hyperparameter sweeps, and model variants we could explore. Second, we focused only on the MatOnto subtask, the smallest dataset. Therefore, our conclusions might not generalize to larger domains such as biomedicine or geography. Third, while we tested several prompt decoupling schemes, we did not perform an exhaustive ablation across all semantic preserving variants. A more systematic analysis could clarify how much variation is optimal. Fourth, the extreme class imbalance makes evaluation sensitive to sampling strategies. Alternative approaches such as loss reweighting or focal loss might yield further improvements. Finally, our evaluation relied exclusively on the official Coltan metrics without qualitative human analysis of model outputs. To conclude, this work shows that prompt decoupling fine-tuning can effectively improve the generalization of large language models in ontology relation extraction. Our experiment with LLaMA 3.1, 8 billion, and LoRa demonstrate that even under strong resource constraints, combining cross-prompt training, moderate contrastive sampling, and domain-specific system prompt leads to measurable gains. Our experiments with LLaMA 3.1, 8 billion, and LoRa demonstrate that even under strong resources constraints, combining cross-prompt training, moderate contrastive sampling, and domain-specific system prompts leads to measurable gains. The best result occur when the model is trained on one prompt formulation and evaluated on another semantically equivalent version. This confirms that LLMs tend to overfit to surface patterns and that prompt variation encourages more robust relational reasoning. For future work, we plan to extend the research in three directions. First, exploring a broader range of prompts templates and systematically quantifying robustness across domains. Second, incorporating structured semantic data during continual pre-training to inject domain knowledge in a controlled way. And third, developing hybrid pipelines that combine LLM-based extraction with human validation and reasoning models, potentially in a retrieval-augmented generation framework. We believe these steps can bridge the gap between raw language modeling and fully reliable ontology learning systems. Finally, we would like to thank the organizers of the LLMs4OL 2025 Challenge for providing the datasets and evaluation framework that made this research possible. Thank you very much for your attention. For any questions or further information, feel free to contact me at this email address. Thank you.